Here we go on Honors Algebra 2, Chapter 4, Section 5. We are solving quadratics, and actually before we start solving quadratics, we need to look at some number sense here. So some review, 6 squared is 36, 6 times 6, negative 12 squared. This square goes to everything it touches. It's touching a parenthesis, so it also goes to the negative. So say negative times a negative, or a positive 144. 0 squared is 0. Here, this square only is touching the x. There's no parentheses. So this is a negative 4 times a 3 squared, or a negative 4 times 9, negative 36. So be careful with your exponents. The squares go to only what they touch. Be careful with the signs. So we start solving quadratics. That's what we're doing in 4-5. And we're going to look at solving using square rooting, and we're going to look at how to simplify square roots. The first thing we're going to look at here is solving a quadratic equation means finding the roots. That's one way. We've already talked about this a little bit. The roots are thought of as the x-intercepts of the graph. So if you want to do it graphically, we're looking at these spots that cross the x-axis. These are the roots or x-intercepts. These are the spots we'll be talking about for the next couple weeks. So we want to solve the quadratic equation here. We're really looking for these x-intercepts. So we can actually write those points. We can write the point 3, 0 and the point negative 1, 0. So these are the 2 points where the graph crosses the x-axis. Similarly here we have the point 1 and the point 3. Those are the x values. So you can say x equals 1 and 3 are the solutions. So you can write them as points. We can write them, just list them as the x values. So let's look at simplifying square roots before we actually start solving with them. So perfect squares, we should know what perfect squares are. We've dealt with them a little bit in factoring. If you look at these perfect squares, 1 comes from 1 times 1, 4 comes from 2 times 2, 9 comes from 3 times 3, and that pattern continues. So the simplest form, when we're dealing with square roots, the simplest form is an expression that has no perfect squares. So we don't want these perfect squares. We also don't want fractions in the radical, and it has no radical in the denominator. These are the 3 things we look at not having to know we have a simplified radical. So the radical sign is the square root sign. So when we have a square root sign, this is the radicand, and it's the radical. So the square root of a product equals the product of the square root of the factor. So the square root of a times b, the square root of a times the square root of b. So we can break this up. So these are some properties similar to the exponent rules that we can use with square roots. So the same thing works with quotient. We can break this up as the square root of a over the square root of b. So we can separate those as their individual roots. So we can use that to help us simplify this. Square root of 27. This actually has some perfect squares in there. 27 is not a perfect square, but 27 we can break up as the square root of 9 times 3, which then can write that as their own root. And the square root of 9 we know is 3, so we end up with 3 times the square root of 3. So what we're really doing here is we're pulling out, or we're trying to take the square root of the portion we can take the square root of. The portion we can't take the square root of, we leave underneath the radical sign. So square root of 40, the thought process of how to break this up is to try to think of perfect squares that multiply to be 40. So for 40, I know that like 4 times 10 is 40. So then the square root of 4 times the square root of 10, I can write it like that, which is going to be 2 times the square root of 10. Now 10 I can break up as 2 and 5, but I don't know the square root of 2 or square root of 5. They're not whole numbers. So this is going to be the simplest form. So we're just trying to pull out the parts we can. So square root of 80, we can break that up. And if you want to do 4 and 20, you can. If you want to use 16, you can try doing that. Most students for this would probably start with 4 times 20. And so you know the square root of 4 is 2. So they have this. Now 20 can be broken up as 4 times 5. So the square root of 4 is another 2. So we have a 2 from the square root of 4 And we also have a 2 outside here multiplied together, which is 4, and then times the square root of 5. So this will be simplest form. Another way to look at this problem is that if you take the square root of 80, and we do it again showing you prime factorization, we can actually factor 80 into its prime factorization and look for pairs. So 80 is, you do 8 times 10, if you remember your factor trees. 8 can be 4 times 2. 10 is 2 times 5. And 4 is 2 times 2. So our prime factorization of 80 could be written as 2 times 2 times 2 times 2 times 5. These are like the bottom of the tree here. And every pair underneath the radical sign is 1 outside the radical side. So we have another pair, so we have another 2. So this is what we're going to have, which is the same answer we already had. So this is looking for pairs. Same thing as finding a perfect square and then taking the radical. We can do a similar thing here with the fractions. We can write that as square root of 5 over square root of 16. And square root of 16, we know that is 4. And look to simplify anything else, we can't. Here, square root of 48 over the square root of 75. Now, we can try simplifying both of these. The square root of 48, we can pull out a square root of 4 times 12 over square root of 75. I would do 3 times 25. So this square root of 4 is 2 on the outside, and I can break 12 up as 4 times 3 again. And the square root of 25 is 5, and I still have 3 underneath here. So then I have the square root of 4 on the numerator still right here, which is 2. So I have 2 times 2 here to be 4, times the square root of 3, over 5 times the square root of 3. And notice how the square root of 3 over square root of 3 is 1, so then I end up with just 4 this. So we can lose all of our radicals there. So we can simplify these, or well, square root of 12, I can just see that as 2 square root of 3. I'm hoping you get to the point that you can break that up and just see it that fast. Square root of 63, 9 times 7, so then it's 3 times the square root of 7. I'm hoping you get quick with it. Square root of 36 I know, so this is square root of 13 over 6. So it should be pretty quick with this. So square root of 54 is 9 times 6 over 3. Square root of 9 is 3, so these 3's reduce out, so I end up with just the square root of 6. Do this one for homework problem. Number 4, just this one. Number 4 for homework problem. So we can keep simplifying. There's a few more rules here we can deal with, some more complicated ones. Square root of 8 I know is 2 times square root of 2, so then I get this, which is 6 root 2. So looking at how to break some of these up. But these aren't too bad. They get a little bigger, but same method. Square root of 108 can do 4 times 27, and then square root of 4 is 2. Square root of 27 is 9 times 3, and I know the square root of 9 is 3, so I end up with this, which is going to be 60 root 3. Same thing. So let's talk about these. These are the ones that are actually more complicated, and they're seen a lot in trigonometry, so be pretty comfortable with these. That would help you out with the trig. But whenever you have a radical and denominator, we try not to have that in simplified form. It kind of gives us a standardized form. And to get rid of that, you multiply by the square root of 2 over square root of 2, which this is a value of 1. We're dividing by the same thing, so we're not changing the problem. We're just going to change the view of it, or what it looks like. So when we multiply the top here, we have 12 root 2. On the bottom here, square root of 2 times square root of 2 is just 2. So that will always happen. You have that you're multiplying two roots that make a perfect square, so you'll end up getting that same number in the denominator. And then the 2 reduces to 12 to get 6. So we get 6 root 2 is the same thing. So we end up getting rid of the fraction altogether. We also get rid of the radical in the fraction. So here we multiply by square root of 5 over square root of 5. And we're left with 5 root 5 over 5. And that's all we can do for this one. But we get the radical out of the denominator. This one looks more complicated, but this would be a simplified form. Here we have square root of 2 over square root of 8 is 2 root 2. 2 is reduced out, so we actually end up with 1/2. And then here, multiply top and bottom by root 5. Multiply by root 5. So we get 3 root 5 over 2 times 5, or 10. And that would be done. So you got to multiply by the value of 1 to get the radical out of the denominator. Now solving. We're going to start solving with square roots. So solving quadratics. We talked about how to solve with factoring last chapter. And we're going to use square roots. That whenever we only have an x squared, in our standard form, the ax squared plus bx plus c equals 0, when we don't have the bx portion, when that b is 0, we only have the ax squared, maybe the c value equals 0. Whenever we just have that portion, we can always use a square root to solve it. So here, if we add 4 to both sides, and to do that, we need to isolate the squared term first. So we need to still isolate the squared term. We need to divide both sides by 2 here. So we get 6 is equal to x squared. Now we can isolate the x by doing the inverse or opposite of squaring. The opposite of squaring is square rooting both sides. And then when we square root both sides, we get the square root of 6, but it's actually plus or minus 6. So let's talk about why that would be. When we have the square root of x squared, by definition, it's actually the absolute value of x, which means it's plus or minus x. That's always true, that whenever you take the square root of x squared, your answer has to have the plus or minus. So be careful, make sure you always include that. Here, we got to isolate the x squared, so I'd subtract 6 to both sides. So we have 2/3 x squared equals -1. Then I'm going to multiply by the reciprocal to both sides to isolate x squared. So we're going to get -3/2. And then we have to square root both sides. We square root both sides here, we find that x is plus or minus the square root of -3/2, which we can write as a square root of -3 over the square root of 2. We can multiply that by square root of 2 over square root of 2, which ends up getting, so we get the square root, plus or minus the square root of -6 over 2. And so this is rationalized, but we have the negative in the square root, and we'll talk more about that tomorrow. For this one, we're going to subtract 6 to both sides, so we get 36, square root both sides, x is plus or minus 6. Pretty simple one there. A couple more here. So for here, we still need to isolate the squared term. The squared term is this whole polynomial squared. So we actually need to subtract 6 to both sides. We have x minus 3, the quantity squared, equals 9. Then we want to square root before we add 3, because the square goes to all of this. So we actually need to square root both sides here. Then we have x minus 3, that's what's left over, the part in the middle here, equals plus or minus 3. Now we're going to add 3 to both sides. So we find x is plus or minus 3 plus 3, which means we have to do 3 plus 3, or 6, or we do a -3 plus 3, which is 0. So you actually have both of those answers are to this quadratic, which makes sense how we have 2 x-intercepts for a quadratic. So here, to get the squared term by itself, we want to divide both sides by 2. So we have x plus 4, the quantity squared, equals 16. Then we want to square root both sides. So we have x plus 4 equals plus or minus 4, and then subtract 4. So a positive 4 minus 4 is 0, or a -4 minus 4 is -8, are two solutions. Let me make up one more here for a homework problem. Let's do 1/2 x minus 2 squared equals 20. And I'm going to have you try this one for a homework problem. And I know you're going to end up with a radical in the answer, but I want you to try simplifying it as you go through the solving here. So solve this one for your second homework problem. We'll call it good, so have a good night.